Okay, welcome to Precision and Significant Figures. This is where we deviate from earth-based science and focus just on chemistry. So this is for you chemistry honor students only. And this is going to be a set of skills that you will be using for the remainder of the school year in chemistry honors. So what is precision? Precision is how close a series of measurements are to one another. It's the repeatability of a measurement. So here you see a target with 4 holes. Now, the shooter did not hit the bullseye. The shooter, however, did get all of their shots in a very close and similar area. And that's where the repeatability comes in. So this is a precise grouping of shots, but there's a problem with it. So here, let's apply the same concept to a scientific scenario. So we know that water boils at 100 degrees Celsius. Now a student goes and boils water 4 times and gets the following data. For trial 1, 2, 3, and 4, they get similar but not exact answers. And the answers are certainly not 100 degrees. So is the student accurate? Take a moment to think about the answer. And they're not accurate because the boiling point of water is 100 degrees Celsius. Okay, let's look at these numbers again. Same numbers. Is the student precise? Based upon that first slide with the target, is the student precise? And you'd have to say yes, because all the boiling points were close to the same value. So if you're talking about their instrument that they're using, the instrument is precise. It just needs to be calibrated to be more accurate. So precision has nothing to do with the accepted value. Sure, you have a precise instrument, but is it measuring the correct reading? Here's another example. Water is known to boil at 100 degrees Celsius. A student boils water 4 times and gets the following data. Trial 1, 2, 3, and 4 all have numbers that are close to 100. Is the student accurate, therefore? You'd have to say yes, right? Because he measured the boiling point to be very close to the accepted value of 100 degrees Celsius. But is the student precise? And again, based upon that first slide, you have to say yes, because he measured the boiling point to be pretty much the same 4 different times. So you've got now a precise instrument as well as an accurate instrument. Can measurements be precise but not accurate? Take a moment to think about that. Can they be precise but not accurate? Sure they can. Look at the target. We already talked about that. Accuracy would be the bullseye, right? So not accurate, hit nowhere near the bullseye. Precise, hit near each other all 4 times. Okay? How about another question? Can measurements be both accurate and precise? Of course, that would be all 4 in the bullseye and each time. Each hit the bullseye each time. Now, can measurements be neither precise nor accurate? What would that look like on a target? What would that look like? Right, they'd be everywhere. Nowhere near the bullseye and nowhere near each other. Virtually every time. This would be like if you stepped on a scale and the scale told you that you were 120, and then you stepped on it again and said you were 140, and then you stepped on it again and it said you were 130. So that would be a machine that would have serious problems. So to summarize, accuracy equals the correct with percent error, and precision is consistency with significant figures. So we're going to actually be talking about both of these, but mainly precision, okay? And that's the title of this. Notes are significant figures, okay? So which reading is more precise? 8.50 grams or 8.503 grams? Which one is more precise? The 8.503 grams, because it has more digits. And that means that the instrument that was used to measure that was able to measure to the thousandths place rather than to just the hundredths place, like in the first number. Now, these numbers are called significant figures. Any number that adds to the precision is significant. So sig figs, we're going to use that for short, represent precision. And they include all known numbers plus one estimated number that's not known for sure. So I'll explain what that means. So in the number 8.503, the digits known for sure are 8, 5, and 0. But 3 is an estimated number. 3 is an estimated number. So there are rules for counting significant figures. 1, all non-zero numbers are significant. All non-zero numbers are significant. We're going to go over all these. We're going to have examples. 2, beginning zeros are never significant. 3, middle zeros are always significant. And 4, ending zeros are significant if there's a decimal somewhere. If there's not a decimal, then it's not, those zeros are not significant. They're not meaningful for precision. So here's some examples. 72.3, 3 sig figs. 699.52. How many do you think? 5, right? These are all non-zero numbers, so they are all significant figures. Okay? How about this? 0.0025. How many significant figures? If you said 2, you're correct. 2 significant figures. How about 0.37? Correct, also 2. Those leading zeros are not significant according to the 4 rules that you just copied down. Also, these beginning zeros are not sandwiched. They're not trapped, captive zeros in between 2 whole digits, so they are not significant. There's going to be some questions about this on Friday's quiz. Examples: 2,507. How many significant figures? 4, right. Because that 0 is sandwiched in there. Same with this one, 60.5. 3 significant figures because the 0 is sandwiched in there, okay? And I do believe zeros is spelled incorrectly on this slide. I did not make it. So anyway, the point is that if a 0 is captive, it is significant, okay? It's meaningful. Now remember, sig figs at the end are significant figures if there's a decimal somewhere. So I think that's supposed to say zeros at the end are significant figures. This right there is supposed to say zeros, I believe. Yeah, that's what this is talking about. So 100.0, there is a decimal. So how many sig figs? Correct, 4. 0.1020. How many significant figures? This one's a little tricky, but if you apply the rules, there's 4. That front one is not, that's a leading 0, not surrounded by whole digits, so it's not going to be significant. How about this one, 100? Is there a decimal? No, so it's only one significant figure. The other 2 zeros are not. The 2 zeros are not significant, okay? So again, that should say zeros at the end of our sig figs if there's a decimal somewhere, okay? So 0.000470, how many significant figures? All leading zeros are not significant, so how many? 3, right? The 4, the 7, and the last 0. How about here? 470, how many sig figs? Right, only 2, because there's no decimal. So only the 4 and the 7 count. It's all weird, but it'll make sense when we start actually using it in this class. Okay, so let's summarize these sig fig rules. The beginning zeros are never significant. Never. The middle zeros are always significant, the trapped ones, the captive ones. And the ending zeros, finally, are significant if there's a decimal, okay? All right, so let's practice. How many significant figures are in this number? Think for a moment. 3. Trailing zeros are not. How about here? There's a decimal now, so what's the difference? The decimal makes them, right? So that would be 6. How about number 3? All of them are, right? The zeros and the digits. 190550. 6 significant figures. How about that one? I don't see any problem with 3 significant figures there, right? What about this one? Are those zeros captive? Sure they are. So every single digit there is significant. Okay, so let's practice some more. How about that one? Are any leading zeros ever significant? No. So how many sig figs? 1. How about that? Number 7. Got a little mix here. If you say 4, you're correct. Ooh, I threw a curveball, didn't I? 1.20 times 10 to the 4th grams. The rule here is the times 10 to the 4th is not significant. The only significant part is the 1.20. And so therefore there are 3 significant figures. How about this one? Same rules apply, so you should instantly know that there are 4 because those trailing zeros have a decimal in the number, 5 point. So that means 4. So do significant figures show accuracy or precision? This was already in our notes. Precision, correct, okay? So how do we round with sig figs? How do we do that? All right, so there's a little trick to get started, and it's something that you would only use pretty much in these notes, or maybe for your homework, which your classwork, I should say, which will be given to you in class tomorrow. But then after that, you're not going to need to use this process anymore. It's very simple, though. So first you underline the number of significant figures you need, and then you draw an arrow to the very next number. Now, if the number, and I'm going to show you how to do this in a moment, if the number with the arrow is 5 or above, you round the last number underlined up. You know how to round. So if it's a 5 or up, you round up, and if it's below that, you don't round at all, right? You just cut it off. So here's an example. Round 91.6, which is 3 significant figures. Round that to 2 significant figures. What would you do? So this is the process, the rules we just wrote down, or just looked at, underline your significant figures and put an arrow next to the last, onto the last one, right? The arrow is just saying, hey, is this one a 5 or higher? And if it is a 5 or higher, then you're going to round that 1 in the 91 to a 2. And the answer will be 92. You're going to be doing a lot of rounding in your calculations in this class, so you have to get this part down, okay? Don't worry, we're going to practice tomorrow. And we're going to practice more today too. So now you're going to round that number to only one significant figure. So you want 1, so you underline, and then the next one you put an arrow. And that arrow is, of course, that number is 5 or above, so you're going to round the 3 to a 4. And that's your answer, 0.004. One sig fig. Now, if the number, again, like I said before, is below 5, you just leave the last number underlined alone. You just leave it and then cut the rest off. So here's an example. If 745.14 was needing to be 4 significant figures for some reason and not 5 like it is now, you underline the 4 that you need, 1, 2, 3, 4, and you put an arrow there, and you just, you see how this gets old after a while, but at first it's useful. That 4 is not a 5 or above, so you just cut it off, and your answer is 745.1. Okay? So, and then you're going to check to make sure your answer is in the same ballpark as the original number. And I'm going to be reminding you about this little trick in answers. If you don't check to make sure your answer makes sense, then you might need to go back and do some more math. Okay? So here's an example. You're going to round 923 to 2 significant figures. Okay? So using our rules, we would underline the 9 and the 2 and put an arrow into the 3. The 3 was not higher than a 5, so we're not going to make it 92, because 92 is not near 923, but 920 is, so the 3 just turns into a 0, okay? How about rounding 8,766 to only one significant figure? Are you just going to cut the 766 off and leave yourself with 8,000? That's not really the same number, is it? It's not quite close enough. However, if you follow the rules, you know that the 7 should round the 8 to a 9, and your answer would be 9,000. Okay, and 9,000 is roughly in the same ballpark as the original number. Okay? So how do we do calculations with significant figures, like adding and subtracting? The final answer must have the same precision as the least precise measurement. Otherwise, we'd be lying. We can't say that our scale or our metric ruler can measure something beyond what its capabilities are. So if I have a metric ruler that has certain increments on it, okay, I'm not going to say that I measured it to the 100th place when I can only measure, if you look here, these are centimeters, if I can only measure to the 10th place. These little lines are 10th lines. So I could be like, 5.55 or something like that, but I can't say it's 5.556. because that last digit would be a lie, because this instrument doesn't measure to that place. That's what we're talking about here. We don't want to be liars. And that's why we have to round. That's why we have to do it correctly. So let's add, and you're going to need a calculators now. So one of the requirements for chemistry on the beginning of last week, on week 1, when we were e-learning only, you were required to have a calculator in your possession. And I'm going to be reminding you to bring a calculator to class. At this point I would already have reminded you. So hopefully you brought one, because you're probably using your phone for taking notes or looking at the guided notes. So 17.12 plus 200.4 plus 74.5 plus 14.555. How would I add these up? What would these be equal to? Now, what's the smallest or the least precise measurement here? That's what we really have to look for. Which one of these is the least precise measurement? The one with the smallest number of significant figures, right? And that would be 74.5. So that means our answer has to only have 3 significant figures, not 4 or more, and not less, okay? So on the calculator, you're going to get this big wild number, 306.575. So you would have to round that to 3 significant figures so that it matches. Otherwise, we would be lying. Again, we don't want to be liars. So the 5 is a 5, the first 5 after the decimal. And so you're going to round the 6 to a 7, and that's how you get that answer, okay? 307. Try this one. 13 minus 0.54 minus 5.366. What's the number with the smallest number of significant figures? The middle one, right? 0.54. There's only 2 significant figures. So therefore, our answer must have only 2 significant figures. On the calculator, you're going to get 7.094. And using our rules, we would underline the 7 and the 0 and put an arrow under the 9. The 9 is greater than or 5 and greater, so we would round the 0 to a 1, and our answer would be 7.1. Let's talk about multiplying and dividing now. The final answer must have the same number of significant figures as the least precise measurement. That sounds very similar to the last few slides when we were adding and subtracting, okay? So let's divide. Calculators, 13.91 divided by 23.3. I should hear a bunch of tapping on calculators in the classroom right now. And you get 0.59699957, a crazy long answer that many students are tempted to write the entire thing down because they're afraid they're going to be wrong if they don't. But guess what? You're wrong if you do, because that has too many significant figures. The smallest significant figures in the problem is the 23.3. 3 significant figures. So we need to make our answer reflect that. So 4, 3, we underline the 3, 1, 2, 3, and then we put an arrow. That's greater or 5 or greater, so that 6 is going to turn into a 7, right? And so we have 0.597 grams per milliliter. And that is our answer. That's our final answer, okay? And the 3 SF, 3 sig figs in the answer because we need the fewest sig figs, okay? So let's practice. 56.7, I only want it to be 2 significant figures. Take a moment to think about that. Right, the 7 rounds the 6 to a 7, so it's 57. How about 87,547 to 1 sig fig? And remember, your answer must kind of reflect the original number. So that 7 is going to round that 8 to a 9. Now, you may be like, whoa, what the heck is that? Well, that's just 90,000 in scientific notation as a little bit of a reminder about what we learned about yesterday. I don't want you to forget. So now the directions did not tell you to put this in scientific notation, but like I said, this was just a reminder that you should be aware of what those numbers mean when you see them. How about this one? 2 sig figs. So that 5 is going to round that 4, right? To a 5. Ooh, same thing there, okay? Maybe you were thinking 0.0025, which is the same exact number, actually, as 2.5 times 10 to the negative 4th. But again, I'm showing you that these numbers have meaning, okay? And multiple uses. we reduced that number, all those zeros. We got rid of all those zeros and we just shortened it. Number 4, 87,547 to 2 sig figs. Last time, number 2, it was to 1 sig fig. Now we want to 2 sig figs. So that 5 is going to turn that 7 into an 8. And that's 88,000, or 8.8 times 10 to the 4th. Either answer would be correct. 1 significant figure. So that 2, a second 2 next to the 4 does not round the 2 up. So it's only 2,000. 1 significant figure, there's no decimal. So those zeros at the end are not significant. Now, had I put a decimal at the end of that, then they'd be significant. We'd have to do like 2 times 10 to the 4 or something like that. Okay. Let's do some more. 3 sig figs, same number. A couple ways you can do this. 87,500 or 8.75 times 10 to the 4th. 29,920 rounded to 2 significant figures. So the 2 and the 9 are the ones we're looking at. And then that 9 is going to round that 9 to a 0, but it's also going to round that 2. It's easy. So it would be 30,000. But 30,000 in this case is not 2 significant figures, is it? 30,000 is 1 significant figure. So we have to put it in scientific notation this time to make this answer work, because 3.0 is 2 significant figures. Even though it has the same numerical value as 30,000, the precision of the measurement is 2 significant figures. Again, this is going to make more sense when we're actually using math to measure things, okay? This is just practice. Little trick here, 25 times 2. How many sig figs is in 25? 2. How many in the number 2? 1. So our answer needs to be in 1 significant figure. And then, of course, now we have units. I threw some units in there. So when you multiply in math x times x, what do you get? Right, you get x squared. So m times m, meters times meters, is going to be a measure of area, like a surface of a tabletop or something like that. So that would be meters squared. And 25 times 2 is 50. 50, 50, that's 1 significant figure because there's no decimal. The 0 doesn't count. You don't have to change anything. It stays the same. Now this one's a little different. 25 times 2.0, now we've got 2 significant figures. 25 times 2.0 is still 50. I just moved the decimal over 1 place, and now I have 5.0. 2 significant figures, but I have to change the exponent and make it times 10 to the 1, okay? Some more practice. 13.5 plus 15.5 plus 173.0, okay? The smallest sig figs are 3 in the very first number, 13.5. So our answer must have 3 significant figures. Okay, so 202 centimeters. And we're adding, we're not multiplying, so we don't put a squared or a cubed next to the centimeters, okay? Let's look at the second one. 85 times 0.223 times 10.3. Put that on your calculator. Quick, quick. I should hear tick, 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 tick on your tabletops with all your calculators going. 85 times 0.223 times 10.3 equals, done. You should be done already. Okay, I mean, you probably got some very weird number. But it should only have 3 significant figures because all of these are equally 3 significant figures. So your answer should only be 3 significant figures, 195 milligrams. Now, number 3, we've got liters plus liters plus liters. And the smallest sig figs is the 75.0, and the 0.350. So your answer has to have three significant figures, 251 liters. Number 4, we're dividing. And the smallest sig figs is what? Good. It's the 2 in 2000. There's only one significant figure. So your answer can only have one significant figure. 0.5, 0.5. The 0 doesn't count, right? Because it's leading. And then we've got adding three numbers, and the smallest sig fig is the first one, 0.002, only has 1. So our answer, after you put them in the calculator, 0.002 plus 23.66 plus 77, and you get 1 times 10 to the 2 millimeters, which is 100, right? Okay. Here's some more. Multiply these on your calculator. Go. I should hear click, 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 click. Only one significant figure. Come on, you can do it. 4. And centimeters times centimeters is cubic centimeters. Centimeters squared. And then we've got 86.5, that's 3 significant figures. So 250 is only 2 significant figures. So our answer can only have 2 significant figures. 789.3 plus 55.5 minus 133.444 equals, what'd you get? And how many sig figs? Only 3, right? Because it's 55.5. So the answer is 711. 711. Number 9, 2 sig figs plus 4 sig figs divided by 3 sig figs. So the answer must be 2 significant figures. And when you do that, you get, come on, slower calculator people. Let's go. I'm looking around the room and I'm looking at those of you who need to be calculating. Come on. Okay. 1.6 liters. And then finally, on this slide, 908 times 0.02 divided by 85.2. Sig figs is 1 sig fig, so the answer is 0.2 centimeters. Okay. Now, this is important. Multi-step calculations. When performing multi-step calculations, apply the significant figure rules only at the end of all the steps. Because if you're making an error or any errors and you're multiplying every step, that error, they will compound. In the end, you'll have a horribly distanced number from the actual number you're looking for. Here's a very simple example. However, in the future, we're going to be doing multi-step calculations, just like the title says. And if we applied these rules at every step, we'd make mistakes. So we don't apply the rule until the very last number, okay? So here we have 3.45 times 5.6 divided by 0.784 equals x over 346. So then we're solving for the x, okay? And we know how to do this. This is basic algebra. So we get 8,526.42857 on the calculator equals 8.5 times 10 to the third, finally, okay? But, or we could get 8.4 times 10 to the third. But based upon the rule above, which value is the correct value? So had we done the calculations, like if we did 3.45 times 5.6 and then we rounded to 2 sig figs because 5.6 is 2 sig figs, and then we divided or cross multiplied by 346 and did it again, we would get one of these numbers wrong. Okay, do you understand what I'm saying? We would get the wrong number. But if we did it only at the end, we would get the right number. So take for a moment 10 seconds and just think back at how you solve this. Okay, and if you follow the direction at the top, you should know what the right answer is, and it's 8.5 times 10 to the third. Okay, that's just one tiny example. We're going to see lots more, and that's the end of this show. We will have a homework assignment on Canvas, or classwork, I should say, available for you when you come into school tomorrow to practice this stuff.